Okay, this is the title of the talk, Open Traffic Models, OTM. So this is a talk about a software that I've written. And so this is, you might say, the debut of the software that I'm presenting to you today. And what the software is supposed to do is it's a traffic simulator. So yes, it's yet another traffic simulator, maybe something that the world doesn't really need, another traffic simulator. But what I'm going to try to convince you of in the next 50 minutes is that this is a traffic simulator that brings some new and, let's say, fresh ideas to this topic. And so hopefully it will be useful to you. Motivation. Why am I working on a traffic simulator? Why has this captured my attention? Why have I put so much time into it? First of all, I'll talk about trends in the transportation world. And of course, we all know that we're living through a very vibrant and exciting time in transportation with a lot of new technologies and a lot of data and services such as, well, gig car share or Lyft or Uber, and we have maps, and so all of this activity has really, I'd say, revolutionized the way that we move, and there is a lot more to come with the promise of autonomous vehicles. Things are going to continue to change very quickly, and they promise to change for the better, but as with any sort of disruptive technology, things it could create problems. And so in this environment, as transportation engineers, we are faced with larger problems, right? Our scope has increased, and we're dealing with larger models and more consequential problems. But at the same time, all of this data that's being generated has not really improved our access to data very much. So we don't have access to the tremendous amounts of data that are available. And also, we've been told that traffic modeling has been basically reduced to this a product that you buy, right? So if you want to simulate something, you purchase a simulator, and you build the model, and you don't have data to calibrate it, and so essentially now you publish something, and that something that you publish is you cannot provide the model because it's proprietary, and the data is either non-existent because it's held in a private company, or it's not provided because there was no calibration that was made. So this is a situation that I feel has really degraded the practice of transportation science. And in this environment where we're confronting larger and larger problems, I think that we really need to focus on repeatability and sort of scientific principles for transportation, for the future of transportation. So reproducibility is one of my motivations. Need for open source models. So into this environment comes a product like Sumo, which is a free and open source simulator, and so it comes as a real breath of fresh air for transportation scientists, and I think that we need more like that. So Sumo is one open source model, and I think we need more variety and more quantity of open source models. We also have a need for large-scale simulation. So as I said, we have larger problems, larger scope. We're solving regional scale, and so there have been movement towards simulating larger and larger networks. And so we have Jane McFarlane here has developed mobility, which is sort of one of the leaders in this area for large-scale simulation. And finally, motivation is what I call a modeling stalemate. So if you recall back in, say, the aughts of this century, people used to have discussions about what is the best model, whether it was a macroscopic model or microscopic model, and this was a pretty sometimes colorful conversation. And that has pretty much gone subsided. And that's because there's been a recognition that there really is no best model, right? You have microscopic models that are good for some purposes. If you look at the dynamics of a freeway, for example, it really is sort of fluid-like. It's characterized by waves. So a fluid model works well there. If you look at urban dynamics, they are kind of queuing-like, so mesoscopic models work well there. And so there is, out of this period, there was really no one true sort of master model that emerged. So, but the people who, but what did come out of this was a study of hybrid traffic simulation. And what is hybrid traffic simulation? This is where you recognize that different models work well on different parts of a network, and you take those different models and you stitch them together, right? So you can take a network and you can partition it, and you can apply different models to different parts. Okay, so this is the problem statement for hybrid simulation. Let's say you have a stretch of road, and you establish an interface between the two sides. So upstream of this interface, you might have a model A, which might be a microscopic model, and downstream you have a model B, which, for example, could be the CTM, a fluid model. And what you're concerned with here is how to design the interface between these two models, which have different representations of traffic. Okay, and well, many people have studied this, although the literature is not very large on hybrid traffic simulation. It's pretty recent as well. But the main considerations that have been recognized is, one, of course, across the boundary, you should conserve vehicles. So the boundary should not be destroying or creating vehicles. The routing information across the boundary should be preserved. And then authors have identified a whole sort of range of different criteria about consistency between the two models. So say, for example, the wave speed might be conserved across the boundary, but these are, I'd say, soft criteria. So these two are hard criteria, and there are a bunch of soft criteria that I'm just going to collect into sensible behavior. And so you could imagine an interface that satisfies these two, conservation of vehicles and preserving route information. So for example, if you just placed a brick wall here, then it would conserve vehicles because no one would go through. It would preserve routing information, but that would not be sensible, right? So because it wouldn't be sensible because with the brick wall, with the interface, the behavior is much different than without the interface. So certainly that's an extreme that you'd want to avoid. But then on the other hand, if you said, I want the interface to have no influence on traffic, that's also not very sensible, because the whole point of doing hybrid simulation was because one model was better than the other, so you wanted to have an effect on traffic. So because that's so fuzzy, let's just call it sensible. Yeah?
So this is micro, right? And this one is macro. Right? So the maximum cut from the micro should be the same as the macro.
These are, except that these are different links. Are you saying the maximum, like the jam density?
No, the capacity coming out, going to the macro should be the same.
There's some capacity here for the interface, which applies to the interface. That's just the capacity of the interface. And it could be determined either by the micro or by the macro.
But they should be the same.
I would
Otherwise,
say,
Jane becomes John and John becomes Tom,
oh,
right?
so that
These
would
are
be
fast drivers,
conserving something
So
about,
higher capacity, you throw into macro, so the capacity should be the same.
right, so
Otherwise, the characteristics are different.
that's
So
something that I would put into the bucket sensible behavior. And that's sort of a
It's not so. That's your
fuzzy
conscious
consideration. So all of things like that. So you could propose an interface that did exactly the opposite of what you're saying, and that would not be sensible. And so you could reject that as a solution. What I'm going to shoot for,
It is obvious, I'm going to do it.
I'm going to shoot for these two. Okay, and you'll see why in a second. So let's see, the people who have studied this. Burrell and Lazort, in 2003, they coupled a micro with a macro, and they noticed, of course, that if a vehicle disappears into the CTM part, then the vehicle that is following it loses its leader, and so then that breaks the model for the follower vehicle because it can't determine its headway. So what their design was to introduce this transition zone, and this transition zone is at least as long as the maximum headway of a vehicle. So any vehicle in this area will always have a vehicle in front of it, and then the trick is then to somehow make the two states, the CTM state and the micro state here, coincide or compatible. So transfer the state from the CTM to the micro. So if you have congestion propagating this way, that would cause lower speeds in the micro, and those speeds would be transferred to the micro vehicles, and that would cause the vehicles behind to slow down. So that's how you achieve the stitching. Berghouten in 2005 then coupled micro and meso, and because these were two vehicle-based models, did not require a transition zone through some magic that they did. And this solution then inspired Jordi Casas from Aimsun in 2011, and this got implemented in Aimsun. So it became available as a commercial product, and they started selling it as, okay, a way to do real-time simulation and decision support. And then in 2007, Leclerc had a very nice little paper where he showed that transition zones were unnecessary. So this was unnecessary when the two models, the micro and the macro, were in a sense compatible. So compatible means, say, Newell's model with the CTM, they're compatible because you can probe the CTM and get information that would allow you to compute or approximate the headways that you need for the micro model. Okay. So that's what that was the observation. Okay, so that's the history. What I've tried to do is generalize that idea and say, let's not define what compatible means. What is the information that one model would need from another in order to implement this boundary regardless of what the models are? So can we do this for two generic models? They can be anything. They can be microscopic, they can be macroscopic, they can be mesoscopic, they can be macroscopic of first order or of second order. And the way I've gone about it is to not consider it as a theoretical problem. So everything about sort of what is sensible, I'm not concerned with. I'm only concerned with conserving vehicles and preserving route information. The reason for this is that once you can put all of your assumptions about the model into a software interface, then basically you can farm out, or you can, um, allow other people to develop the models and provide them as plugins for your software. And if those plugins are not sensible, in the sense that Alex just described, then nobody will use them. So it's like it becomes a market mechanism, what is a good model and what is not a good model. So all I'm trying to do is provide the framework for allowing models to interact this way. So is this possible? Can you take all of the assumptions about these two models that are needed to make them interact, put that into a software interface, and then design a protocol that will use that interface and through a mediator to exchange information between the two models such that such that you can stitch them together in this way. So I'm not concerned with the behavior being sensible. That's something you won't hear very often. Okay, a little bit of terminology. First of all, OTM provides for building road geometries, and those road geometries will include road connections. So road connection is a mapping from upstream lanes to downstream lanes, and what it means is that vehicles going from these lanes can turn into these lanes. So it's pretty obvious. And then lane groups are groupings of lanes in a link. So this is a link, this is a link, and this is a link. And we group lanes, adjacent lanes, into lane groups in a way that all lanes are included in lane groups. So the lane groups cover all the lanes of a link. Those are two terms that I'll use. Next term is a flux packet. So a flux packet is the thing that is being sent over the interface, over the boundary. And what it tries to do is to abstract the state. So each model will have its representation of the traffic state, and that gets wrapped into a flux packet and gets sent. So can we create a description of state that is generic enough that it can capture meso, micro, and macro? So let's say if the model is a vehicle-based model, this is what the flux packet would look like. It's essentially a table where one entry is the type ID. So let's say type 0. This is, a type can encode, for example, whether it's a car or a bus or a truck. It can also encode whether, say, what lanes the vehicle has access to. So if it's an HOV vehicle or a single occupancy vehicle, it can encode whether, say, the vehicle has access to certain data, so if it has an app or not. So any additional information that then the model can look up with this ID into a lookup table that is provided by OTM and get this additional information that it needs. So that's the type ID. Then there's a path ID. So these vehicles here, this bit of state, this is a chunk of state that is of type ID 0, and it's traveling along path 7. So similarly, the model can query OTM and say, what is path 7? And OTM will then return the links on path 7. So this is the routing information. In this case, for this vehicle of type ID 1, it doesn't have any path information. What that means is that this vehicle is routed probabilistically. So whenever it reaches a sort of a bifurcation, then there's a probability distribution on the bifurcation, and it samples that probability distribution and decides which way to go. So this, again, is functionality that is provided by OTM, and it's not implemented by the models. So in this case, the state of a vehicle-based model is some number of vehicle objects. So the flux packet is a wrapper for a bunch of vehicles that gets passed over from one model to another. If the model were a first-order fluid model, in that case, the state objects would just be numbers. Right? They'd be floating point numbers, so something like that. If it were a second-order model, like on a generic second-order model following Lebac's terminology, and Lebac's identifies this additional state I, which is sort of generic, and he shows that this just advects through the stream, and with different representations of I, you can capture different second-order models. For example, the ARZ model, the Colombo model, and you can apply a Godunov scheme to this second-order model, and it turns out to be something very similar to a Godunov scheme that you apply to the first-order model. Did you have a question? Okay, so the rows are just different instances, or not instances, but entries in the table. So this flux packet is being passed over the boundary from one model to another, and it contains 4.3 vehicles of this type along this path, and 0.3 vehicles along this type, but of a probabilistic path. Yes, yes, and that happens at some instant, and at the next instant it passes another. So the communication between the models is in terms of flux packets that are being sent. Okay. So did you have a question?
Yeah, can you show me a 0.3 vehicle?
Well, this is, say, a first-order model. This is like the CTM. So in the CTM,
And you have fractional vehicle.
yeah, of course.
Of course.
Yeah.
You can show on their own fractional vehicle.
Sure, and then this, but what happens if this gets sent to a vehicle-based model, then the vehicle-based model can only instantiate 4 vehicles, and then it has to have a buffer to preserve the 0.3 vehicles, so that when it gets its next flux packet, it can complete those. So that actually is administered by OTM as well. What I was going to say was that these two, the sort of canonical numerical methods for them are Godunov schemes, and they're very similar between the two. So if I can implement a Godunov scheme in OTM, then it may cover both the first order and the second order model, and I think that's what is actually happening. Okay, so let's look at the protocol. You have an upstream lane group, and then there's a road connection that leads to a downstream lane group. And the upstream lane group at some point tells the software, I want to send a packet, a flux packet P, along road connection R. And so it tells the mediator this, it sends an event. And the mediator says, okay, well, road connection R connects to this downstream lane group, so it asks the downstream lane group through the interface, the software interface, how much space do you have for packet P? And it gives the packet P to the downstream lane group. Then the lane group responds, well, it looks at the packet and says, I have this much space for this packet. It may actually fit or it may not. And it returns that value to the mediator. And then the mediator compares how much space it has with the actual size of the packet and responds back to the upstream lane group. You may send a portion alpha of this packet. It may be between 0 and 1. And so the upstream lane group says, okay, well then I'll send a portion alpha and gives it to the mediator. The mediator passes it to the downstream lane group. So you can immediately see the sort of the parallels between something like this and the CTM, right? Where the CTM is saying, I have an amount of space, that's your W times rho jam minus rho, right? And this alpha is just comparing the supply and the demand and is computing the minimum formula of the CTM. but the interesting thing is that this scheme, this protocol, also can be used for vehicle-based models. So if this was a vehicle-based packet, then the alpha could be either 0 or 1. You can either accept the full vehicle or you can reject the full vehicle. Okay, so it fits into the scheme. And even more so, the second order model, the second order Godunov scheme, fits into this protocol, because the only difference between the second and the first order Godunov scheme is that to evaluate x, they needed to know the packet. So that's why in the first order scheme, I can evaluate my supply without knowing what's being sent. Those are two separate things. But in the second order, they're not separate, but we capture it by sending the packet forward. Okay, so the claim here is that this is a generic protocol that captures vehicle-based first order and second order models. Okay, but it's a very simple case. That's just the one-to-one case. Then there is the many-to-many case. And so that is, and when the requests to pass these packets forward happen simultaneously, then you have the sort of collision of requests, and that is the topic of node models. How do I now reduce packets amongst many centers? So this is a typical intersection. There will be 12 upstream lane groups. So the set of upstream lane groups I call here G. They're connected to 12 via 12 road connections to 4 outgoing lane groups. And so you can construct from here, you can construct a graph like this, which is basically saying where the demand is going to and via what road connections. Okay, so on top of this structure, and this is inspired by Matt Wright's work of Laser Koinum and Alex here, but basically a generalization of what they did, adding the road connections piece. What you have to do is, provided all of the demands on the lane groups directed towards all of the road connections, and provided all of the supplies on the downstream lane groups, what are the flows that are actually going to go through the network? And so this is sort of a complicated part of it that I won't focus on too much, but there are basically the algorithm looks like this, that while you haven't finished, you have to do all of these steps. The node model step 0, then you evaluate this termination condition, which don't even worry about the notation, is horrible. But this is, and then you do steps 1 through 6, and you repeat until you terminate. And you can show that this will terminate within a small number of steps. So the first step is you initialize and you see what lane groups are sending, have demand on them, and which ones have supply. This termination condition basically says that you break if all of the upstream lane groups are either empty or blocked. And so you initialize that here, and then you pass the demand from the upstream lane groups, you pass it to the road connections, then you pass it down to the downstream lane groups, and if those demands exceed the supplies, then you calculate these reduction factors. Then these reduction factors get passed upstream via a first in, first out assumption to the road connections. Then the road connections pass them back upstream to the lane groups, and then all of those reduction factors get applied, and you get a little bit of the demand gets now sent back downstream to the road connections, and finally to the downstream lane groups, and then that is used to reduce the supply in the downstream lane groups, and then you repeat until you converge, until you terminate. Okay, so that also operates at the abstract level and does not have to be implemented by any of the models. So the models can focus on the dynamics within the links. Okay, and they don't have to worry about routing or any of this node model stuff. This is provided by OTM. Okay, so this is how I conceive of OTM. So you have this framework here, which has a modeling interface and has a control interface. So these are a set of methods that you have to implement if you want to build a plugin that's a modeling plugin. And so let's say there are all these modeling plugins that are out there, and so you download them, and say you have a plugin for the CTM, a plugin for Newell's microscopic model, a plugin for some queuing model, and you plug those into OTM. Also, then there is an interface for controllers. So people build their little controller interface, and you plug those in. Then you have a configuration file, which basically says what plugins you want to use, what models you want to use where in the network, and how you want to configure your controllers, and you add that to OTM. You open that in OTM. OTM then has an API which allows you to use sort of high-level programming languages like MATLAB and Python to control all of this. And so you through these languages you can run, you can control, you can rewind and so forth, and run a lot of stuff. And then you can also then take an OTM simulation and you can send it to a high-performance computing service like NERSC or Exceed, which are available on campus. Okay, so back to what it means to be a model that works in OTM. If you are a plugin and or a traffic model and you want to participate in OTM as one of these plugins, these are the two things that you must do. You must implement the OTM interface, right? So, for example, we saw before the protocol is going to ask you how much space do you have for this packet. You have to be able to provide an answer for that. Now, I don't care what answer you provide. It could be a really lousy answer. That just makes you a lousy plugin, and so people won't use it. But there are the interface is more than that. It's also methods that are used to, say, compute performance metrics, implement control, and the modeling interface. Also, the promise that you have to make is that you will only produce packet release requests that are consistent with vehicle routing. And what do I mean by that? So remember that the packet release requests were produced by a lane group onto a road connection. And so you have to promise that you will only send packets along road connections that are consistent with the routing information of that packet. So you never say, if there's a packet that's on this path turning left, you will never send it along this road connection. Well, that would get flagged and then it would produce an error. But this has some consequences because once a packet, let's say a packet got sent along this road connection, now it's added to this link. This link has a particular model. The next thing that's going to happen in OTM is that it's going to see, and let's say this packet did not have routing information. So it's of the type that samples its next link. So when it's here, it's going to look at this node and see that there is a split. And let's say the probability of going this way is 10%, the probability of going this way is 90%. So it'll flip a coin and it will decide what is its next link. So if it was added to this lane group and this is its next link, then within this link, it's going to have to change lanes to get from this lane group to this lane group so that it can access this road connection. So a consequence of this requirement is that any model that participates in OTM must have some sort of lane changing strategy to get packets into their target lane groups. Okay, so you have to have a lane changing strategy. Okay, the other part of OTM is that it's supposed to enable sharing and reproducibility a little bit better. So what would be really great is if you could take a network and switch one link from, say, micro to meso, or just select very quickly and switch the models that are applied to each link. But for that to be able to happen, you have to have a common representation of the network that at least includes the information that you need to run these models. Because if I were to replace one model with another, but that new model required new information, then I wouldn't be able to do that. So OTM provides a sort of a data description for traffic simulations that tries to capture everything that any model would need, but let's say a maximum common divisor of that information. So there may be models that need additional things, but this is the minimum amount of information that you absolutely must have in order to run. And that includes the graph connectivity, the road connections that I mentioned, some parameters for the road, and here I only require that you provide the capacity, the free flow speed, and the jam density. So something compatible with the triangular fundamental diagram. Something about the geometry of the road, so whether it has turn pockets, and then some description of the demand. Here I said commodities, I really meant the different types, so that appeared in that table. So that lookup table for the types has to be provided. The routing options, so whether demands are path-based or split ratio-based, and they can be both at the same time. And you have to provide whatever control structure you'd like to. So the road geometries that are supported this would be something very generic, is where you have two complete lanes, and then you can add these sort of side partial lanes for a turn pocket, or this could be the termination of an HOV lane or something like that, another turn pocket. So you can build this in OTM. Also, another sort of geometry is for HOV lanes, where you can define gates in the HOV lane. So this is a network description that is similar to what you find in other simulators like GameSun or Ceramics or Sumo. So I think that what you could do there, you could probably do here. This is, I mentioned, road parameters. You provide 3 for each link, and they can be interpreted according to the model that you're running on that link. So let's say this F bar could be interpreted as the capacity for a macro model, as a service rate for a meso model, a capacity for a micro model, but I say that even though most micro models don't have a sense of capacity. But if you did, like in Newell's model, there is a sense of capacity, so you could include it. And so by using the same parameters for the different models, I think it addresses a little bit of what Alex was saying, about the compatibility between the models. Then you also define the control infrastructure. So here, let's say you have your network, and you can apply to that network all of the sensors, which, you know, they're like little probes into the network, and the actuators. And this is part of the infrastructure. And then you define a plugin that basically registers with the sensors and registers with the actuators, and then applies some algorithm to go from the sensor signals to the actuator signals. And this is also done via an interface, so you can build a plugin for it and distribute plugins. Okay, available models. So just because this is a proof of concept, I built the 3 canonical models, which are for macro, the CTM, for meso, this 2Q model, and for micro, Newell's simplified microscopic model. And so this is just a summary of the sort of the attributes of these models. As I said, any model that participates has to have some sort of lane change model. So I implemented Laval's ideas from a 2006 paper. The longitudinal dynamics is just standard CTM, and you know, the interface that requires that you report available space to an upstream model is just reporting the supply in the upstream cell, in the most upstream cell. The 2Q meso model has a lateral dynamics which is trivial. I just say, instead of trying to change lanes somewhere along the lane group, I just put the vehicles directly into their target lane group, so I ignore lane changing. This model consists of 2 queues. One is a waiting queue that basically simulates the transit time, and the other is, I'm sorry, this is a transit queue, and this is a waiting queue, which can be controlled by a signal. It's service rate. And then finally, there's Newell's microscopic model, which again, the lateral dynamics I trivialized by just putting the vehicles straight into their target lane group. And the longitudinal dynamics is, you can look it up. This is the equation, and I've added here just a term for capacity. And the available space is the jam density minus the total number of vehicles. So this blocks when the total number of vehicles reaches the jam density. And then it says the space is 0, so it blocks new packets entering. Okay. So a few small examples. Oops. Let's see if this works. Okay, so these are pure models. This is a pure CTM with a large time step, and it has a bottleneck here, so you see that the congestion starts to accumulate. This is a finer grain CTM. This is that a 2Q mesoscopic model, and these two numbers are the number of vehicles in the waiting queue, number of vehicles in the transit queue. And you see already some difference in behavior between the macro and the meso, which is that the meso, it applies the capacity at the end of the link, and the macro is applying the capacity at the entering end of the link. This is Newell's microscopic model. You also notice that I'm applying the same demands on all 4, but the queue on the meso doesn't accumulate as quickly, basically because this accumulates a jam density, so it's much more dense. The queue is denser, right? So it doesn't go as fast. So this is just single vehicle dynamics. Now this is putting the interface between an upstream macroscopic model and a downstream microscopic model. And here the downstream is the mesoscopic model. So you'll see that when the queue reaches here, then it starts rejecting the flux packets, and the congestion propagates into the upstream. And this is the opposite. Now these vehicles are sort of just disappearing. They become little clouds of fluid as they go into the CTM portion. And It's actually kind of neat to see. Okay, so this is the simplest case. This does not involve the node model at all, but this can actually now, once you have the abstraction of an interface, the obvious thing to do is to take this to HPC. So because in HPC what you want to do is split the network into small chunks, and then each chunk assign it to a process, and those processes communicate by sending messages to each other. So we've already figured out by doing these interfaces how to construct these messages and what should be the protocol for sending the messages, regardless of what is the model that's running. So we did that. We split the network into many pieces and passed flux packets between processors. Last summer, I put together a proof of concept, which was focusing only on a CTM, so the purely macroscopic model, but just because it was easier, and this was a proof of concept, we used standard tools for partitioning and for communication between the processes, and we did not have any control elements in this proof of concept. Whoops. So we took a model from of the I-210 in Los Angeles. In this case, it was split into 4 pieces, and that determines what I call a metagraph, and each node on this metagraph represents some chunk of the network and is running on a single processor. So in this case, it was 4. But what we did was we started cranking up the number of processors. So for the serial case, this was a really large network, so it took, for some, it took 11 hours to load. So that's probably because it was running into memory issues, but it took 4.5 hours to run even. And as we went to 2, 4, 6, 8, up to 1,024 processes, the times really came down, and if you focus in here, at 1,024, we were loading in 8 seconds and running in 19 seconds. So the speed up is pretty fantastic, and also this green line here is the communication, the time wasted in communication. And still, that is relatively low with respect to the runtime. So the rule of thumb is that you can keep on adding processors until these two become comparable. So I think we could have even gone to 2,000 and continued to sort of juice this system. So that's when, you know, I was very happy that this had been successful. I think that where it would be a good idea probably to take this to the next level, which is do it not with the CTM, but with a model like Sumo or something. So in conclusion, I mentioned 4 motivating factors for this work. And the first had to do with trends in transportation. And how does this work address the trends is that allowing for many models to participate in this open source framework will improve the shareability of models. Okay, so you can distribute models, and you can publish your models, and this will increase the reproducibility of results in the literature. We need more open source models, so this is an approach of a model as a plugin, large-scale simulation. If you can participate in OTM, then possibly we can have a path to HPC, free path to HPC for any model that can participate in OTM. And the modeling stalemate, I think, is addressed by just more hybrid traffic simulation. So just, you know, no need to bicker. There are enough toys for everybody. So let's just do hybrid simulation. This is where you can get it. It's all in GitHub. It's all open. You can go right now if you wish, and if anybody is interested in working more on this, as I said, this is its debut. There are already a few people who are using it, but I'm very happy to work with anybody who's interested in pushing this forward. So thank you for your attention, and I'll take any questions. Yes?
How do you propose to analyze the results that you use multiple models?
That's a great question. So a part of the interface that I didn't talk about was that there are performance metric calculators that use interface functions to query the results from the models. So the models have to implement these functions, and they're things like, give me your density, give me your travel time. And so the calculator just goes through all of them and calculates those quantities on the performance metrics. Yes?
No, it seems like things are simplified and you see what roundabouts can do. You try to roundabout.
I have not. Yeah. And, you know, I've been asked that question before, and it's stumped me before. I really don't know exactly how to bring roundabouts, which are somewhat complicated. But there are many ways that you could model a roundabout. And what this allows you to do is sort of just test those different ways. So you could think of a roundabout as, say, just like a complicated node with a state, it accumulates vehicles at the most aggregate level, or you could think of it as actual road segments, and those road segments accumulate vehicles. So there are different possibilities for how to.
You got a bunch of T intersections for the road, people only come to the right all the time.
Yeah. Yes.
Have you thought about making it so that they can kind of adapt to the best model? I assume it's kind of a runtime, trade-off between runtime and fidelity, right? I mean,
Well,
it's
yeah,
using
yeah.
this
So
model,
this, I haven't put much thought yet into how to use this and what are all the nice applications of. So, for example, I haven't benchmarked all of these models, and I haven't taken sort of the microscopic models to HPC. So there's a lot of stuff that this opens sort of new potentials for comparisons between models and so forth. All right. Well, any other questions?
Can we see the movie again?
Yes, the movie was the best part. Okay,
Yeah.
thank you very much. Yeah. Oh, is there a question attached to that?
Yes, it's a question.
Okay. Which,
Not this movie, the previous one.
this one.
It's one before that. This one.
This was the pure.
Yeah, the view. So you can see that micro guys chew earlier, clear earlier, as opposed to the other guys. They have the same capacity, right?
Yes. So that's a good point. So
So these guys will chew more, same demand, same capacity, they chew more. Right now, I'm about the same. So
let's go.
what's the clearance now?
Yeah.
The clearance is they drive like hell and clear much faster than the macro over there. The same people, same capacity, same speed,
Yeah.
same demand.
Yeah. So let's see. I'm going to. So the answer to your question is that there are random variations in the micro. So this is fed by a Poisson process, and so you always see some random variation. So maybe in this instance, it was a little bit different, but I'm sure if you did this over many times, on average, you would find that, so let's see, this cleared at exactly 2,037 seconds. This cleared at 2,160 seconds.
The top one.
This one cleared at 2,143 seconds. So these are differences of 100 seconds. And so you'd have to do this over an ensemble, take the average to conclude that there is some significant difference in the clearing times. So that's that. Yeah.
Thanks, Gabriel.
All right. Thank you.
On behalf of Transoc and ITS, we just want to thank you for your work.